Everybody is welcome, ladies and gentlemen. Today we want to look at regression diagnostics. Regression diagnostics. We have learned how to do OLS regression, classical linear regression, multiple regression, dummy variable regression. We've done it. We've done a lot of things, but we need to verify that our data is sensible. We need to verify that our analysis have met the assumptions of regression. We need to be sure that we've not made mistakes. Some of the assumptions are linearity, that there must be a linear relationship between the independent variables and the dependent variable. And this will be reflected in the residuals. Normality, homoscedasticity, multi-collinearity, independence, autocorrelation, indigeneity, errors in variables, model specification. All of these assumptions, we got to kind of make sure that they are accessible. But you see, you don't want to bog yourself that every paper you are writing, you have to be checking this. There are some few ones that we have to really, really check. And other ones, we don't have to bother ourselves much. But for this exercise, we'll do most of them. And then along the line, I'll tell you which ones we have to bore ourselves with. So once again, you're cordially welcome. Now, though there are certain things that are not assumptions, but you have to sometimes check. Some of them include influential variables, variables that are influencing the movement, okay? And I've given you some links here for you to go and watch some videos related to influential variables. Outliers and influencer. First, what's the difference between an outlier and an influencer? Who can raise a hand and tell me? What is the difference between an outlier and an influence? An outlier and an influence. An outlier and an influence. In fact, let me try and show you some graphical interpretation of something, okay? Now, let's assume that we have something like this, okay? We have this beautiful something here. We have this line there, okay? And then we have that line there. And then we have some observations, okay? Let's get some observations like this, like that, like this, like this. Okay, so we have this, okay, and you have your Y here. Oh. You have your Y here, and then you have your X there. And I can create another situation. Okay, I just want to create another quick situation like this, and then that. And then once again, in this situation, we have this. We have this, that, and then you have this. Okay, so my concern, ladies and gentlemen, my concern is this very variable. Okay, this one there, this observation, and then in this context to this observation. So you have your X and then you have your Y. So let's call this panel A and then this one panel B. And we are talking about influential variables and outliers. A and B, which one is an influential variable? And then which one is an outlier? Just raise your hand and tell me if you know. Which one is an influential variable? And then which one is an outlier? A and B. Okay, so we have Portia Mensa. Portia, just tell us, which one is an influential variable?
The B is the influential, and the A is the outlier.
Okay, obviously, you know I'll ask you why. You know I'll ask you why, right? Oh, she just said that and left, expecting that, you know, I will not tell her to give reasons why. So please, unmute yourself and tell us why. You know very well you have to give us a why.
Okay. Hello, Doc.
Continue, we are listening.
Yeah, the B is the influential because the point, it has a large effect on the slope.
Why do you say? Where is the slope?
It's like I
haven't drawn the slope, so where is the slope?
No, the point here might have a large effect on the slope that you draw.
Why do you say might have a large effect on the slope that I will draw?
Because looking at the data inside, the variables inside the B.
All right. You are speaking, just that you are not speaking convincing. But all the same, thanks for your point that you've raised. Who else has something else to say? Who else has something else to say? Influential, in fact, she's right with what she said. Okay. And those who are commenting have interesting marks. Okay. So an outlier is an observation with a large residual. An influencer is an observation with a large residual and whose removal substantially will change the results. So let's say you're talking about people who are at your ages in this class. And then all of a sudden I mentioned somebody who is 90 years. That 90 years can drive the mean. So if you should remove that 90-year person, the mean can change. And so when you go, in fact, she's very right with the point she made that when you go to this data and you want to actually draw a regression line here, okay, if you really, really want to draw a regression line, there's something you can do. This is a regression line that you draw. And this regression line, it will pass through the data set and it will still be sitting or closer to the observation at the top here. It will be closer to that observation at the top. And so in such a case, this one is still part of the mean, more or less. But then when you look at this, if we draw a line here, the line will still go up that way, positively related. But you can see that this will drag the mean towards itself, okay? So the relationship between this observation and the mean, okay, it will drag the mean. So if the mean is there, it will now pick the mean and then it will push the mean towards itself. And the reason why it's doing that is because it's what? It is an influencer. So this is not just an outlier. So an outlier is having a large data set, but it may not influence the observations. But an influencer is an outlier that is dragging the mean towards a certain angle. So B is indicative of an influence, okay? So it's very important to check whether your residuals are exhibiting those situations. So influence can be thought of as a product of leverage and outlierness. That is it. Influence is more powerful. And there are two types of methods for assessing outliers in a regression: statistics such as residuals, the leverage, the Cook's distance, the defects, all of these are used to check whether there are outliers in your data. So you've done a regression, you think you are going, everything is going fine. Sometimes even the results that you are getting are not good results. you need to check for these. Okay. So are there outliers in our data set that we have? Let's try and see whether there are outliers in our data set, okay, by installing Dr. Fox's car package. So let's go to our R. And then we try and install the package. Now, in case you guys do not have your information, I will encourage you to try and then have your information. Okay, your information is very, very important that you have. So this is a data set that I have. Okay, and what I'm going to do is I'm going to show some graph. Now I need to remind myself of the regression. So in order to do that, I'll just go up here and I'll run my regression again. In case you are with me, you can do the same thing by running your regression. I've highlighted the regression that I'm running. Okay. Oh, okay. I need to install my data set. I can run the old regression or the new regression. Okay. So I'm just running this old regression, this new regression. So in my data set, you can see the regression that I have run there is down here. And in this regression, everything seems to be fine. The price seems to be interesting. This was a regression that we did, and then we're able to show some interesting results eventually. Now, we are going to check the residuals, okay, of the data. And we do that by installing this library car package. Okay, this library car package. And for those of you who might not be seeing it well, I will just show it to you here. So you type the command library car and then load the package and use this command, which is par info, which is going to help us to put all the plots we are going to draw now. I'm going to draw the entire plot, you know, by a 2x2. So we're going to have more plots in one screen. So you use this command to do that, and you plot the results. We are going to plot the residuals against the fitted, and then other aspects, and then check whether the possibility of outliers or influences in the data. So let's try and do that together. Okay. So those commands I showed you earlier, those are the commands. Let me just export this slightly and then show you how big it is. All right. So if you look at what I'm seeing here, that is, if you can look at that, okay, then I hope you can. Sometimes I just want to make it slightly bigger. Okay, so let me make it this bigger. Yeah, it looks bigger. It's gone. All right, let's use this. So if you look at this data, the first thing that you see here is the residuals versus the fitted. And you will notice that you have a line that is going up and down. We've seen this. Look at some of the observations. They are not closer to the fitted line. The residuals are hanging around the fitted line. Now, the key observation is at the top there. And that observation is observation number 24. It keeps showing itself. 14, 24, 34. See, they keep showing in the normal contact probability plot, they keep showing themselves. Then the location, when you look at the location, the observation 24 and then 34 appears to be again showing themselves. When you look at the residual versus the leverage, again, those guys appear to be showing. So it might be nice to just have a look at that particular observation. So this graph gives you a picturesque understanding of the residuals and how the residuals are behaving and whether a particular variable may be an influential. Now, it is a likely situation that this might be an outlier, but you need to just go deeper and then check the situation carefully. As far as those observations 14, 24, 34 are concerned, okay. Once you do that, you can now be able to get a better understanding. Let me just show you this again in our slides. So this is it that you have in the slide. And I've given you another example for you to watch it on YouTube, okay, about these residuals. Okay, so look at observation 24. Now we're going to do something we call AV plots. And the AV plot is some added variable plot. And it sometimes gives, again, another kind of picturesque understanding. So this is first graphical touch to determine whether they are outliers before we even go and do the other ones. So let's run that AV plot to see. So I've done the AV plot here. Now you can see my AV plots there. And it's very interesting because the AV plot is likely to reveal some interesting things. Okay. So for example, you have the quantity demanded on the vertical axis and then the price. So it is showing the relationship between each particular variable and the dependent variable. Okay. So this is quantity demanded and complement price, quantity demanded and income, quantity demanded and blah, 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 blah. But look at the religion Christian. It shows a positive link. It kind of shows a positive. You can see that for religion Christians there. And in each one of them, check what observation 24 is doing there. Okay. Observation 24 again seems to be kind of showing himself as a little bit of a stubborn guy. Okay. Everywhere we go is 24-17, 24-17, 24-17. It keeps showing. So again, it gives you a better understanding of some two variables, two observations. That seems to be a bit of problem children. But again, you can't conclude that because of that you're going to remove them. Okay. You just have to examine it. You have to examine it further. All right. The next thing is the command called AV plus with some specific, observation. So what this command, let me just show it to you here. What this command is indicating is that we're going to run this command and it's going to show the leverages, outliers, and influences. Okay. So what it's going to do is to label each observation on the plot. Okay. And then it will ID the most influential observations. Okay. And it will tell you the font size for the ID, okay, which we will use in the graph. So let's try to run that command and then you see what will happen. So when we run that command, okay, when you run 8 hours, well, it appears that we don't have much to tell. Okay, it appears that we don't have much to tell. So we'll go to the final aspect of testing, whether there's truly an outlier. And that final aspect of testing, whether there is truly an outlier, is this command, outlier test for our data set. Outlier test. So we're going to do this outlier. The test is a Bonferroni test for outliers. And the clue is simple. If the unadjusted R-square, if the unadjusted p-value is less than 5%, then there may be an outlier. And it will flag the name of that observation. Okay. Okay. So if it is less than 5%, then there is an outlier. If it is not less than, it's rather bigger than 5%, then there's no outlier. So we've already kind of have a feeling that observation 24 and 17 might be a problem. The question is, are they truly a problem? Okay. Well, the outlier test will tell us. So let's go and run this outlier test. And to do that, we just run this command and you can see the results here. Okay. It's a little bit difficult to zoom in. I don't know. When I zoom in, it appears that you guys don't see. However, the values that I have here are interesting values. You see, it says that no studentized residuals with Bonferroni, p-value is less than 5%. The largest residuals, nothing. Okay, our p-value is 7%. Okay, so it shows clearly that there are no outliers, because if there were, we'll have a p-value which is less than 5%, and ours is 7%. So it means that in ours, there's no p-value. So when you are writing your analysis, you indicate that we did a test for outliers and there was no outliers that were detected. Then you quote into bracket, you give the values for the studentized unadjusted p-values, you give the values for all of that. The Bonferroni p-values to indicate that you've truly done that. Okay, now that is that one. There is another one that will tell you whether we are actually doing outliers or not. And that is this command, okay? That is this command. Again, this command will tell you those ones that may be influential. So we have the studentized residuals here. We have the hat values there. And the beauty is that, again, 24 seems to be showing interesting signs, but already we have the test that has already told us that there's no big of an issue right there. But more importantly, look at the influence plot. And what it does is that it lists those values, okay? Each one of them, the hat values, and then the cookie distance for each one of them. And again, it appears that, there is no big of an issue, okay? It seems that 25 rather may be an issue, but it's not a big issue based on the previous results that we have. Okay, so again, it doesn't show a big of an influence because we didn't even have an outlier. So I'll come back to your questions. Observations that are unusual for at least one of the influence measures will be highlighted in the next graph that we'll draw. Okay, so in fact, this is the one I like the most. Look at this last command, okay, in the command window. It says potentially influential observations. And what did it say? None. Potentially influential observations. Then he wrote none. Okay, so it tells you that there is no influential observation, okay, that is there. So once again, we use several means to check whether there is an outlier. And interestingly, there isn't any outlier. And this is one thing. So guys, so what if there are problems? What if there are influential observations? What if there are outliers? What if there are influential observations? Well, there is a way you can handle that by using a robust regression. Okay, it's done by an iterated ray-weighted least squares. Okay, and it uses something we call Huber weight. When you require this foreign package and the mass package, the robust regression is an alternative to OLS regression when the data is containing a lot of outliers or influentials. And it can also be used for the purpose of detecting influential variables. So whenever you have such a situation in there, don't worry, run your OLS regression and also run this robust regression to let the reader know that actually I'm doing this because there's there are outliers and influentials. So I want this to correct them. And so you can do that. That is if the outliers are there. So what we are going to do is to run the foreign and the mass package. And then I'll run my robust regression like this. So this is a robust regression I've just run here. And the most important thing is you can see the results of the values. I want to show you something if you can see it well. You can see the price value is negative 8.1. I want to run it to one decimal place. Negative 8.1. Now, if you can remember, our price was negative 3.17. The robust is indicating what? Negative 8.1. 0.1. So that again shows that it appears that some things interesting are happening here. Some of the things that were negative before are positive now. Okay. Some of the things that were negative before are positive now. And I wish I could show the p-value for this, because when you show the p-value, what I have is a t-statistic. Okay. The t-statistic. I don't know the actual critical values, but the p-values would have helped to see clearly that indeed there is a situation of significance. But for me, what it just goes to show is that even if there are outliers in your data, you can have something that can deal with the outliers in the data. And that's what we just shown. That's all that we've just shown with this robust regression. So keep it in your mind, one day when you have such a situation, you can handle that situation with a robust regression. So guys, outliers, influencers, we are done with that. We are done. We are now at that diagnostic check, which is the assumption of linearity.